Hey everybody, welcome back to Organic Chemistry. My name is Todd Rothman. In this video, we're going to go over mass spectrometry mega review. So basically, this video is going to cover all the key details that you need to know for mass spec. Let's get started. First off, I want to talk briefly about the general apparatus. What do we do? And just a really quick, crude drawing that I put together just so I can get the points across. So essentially what's happening is we have this vaporized sample on the left, and it's passing through this tube. As it passes through the tube, we're going to have an electron, a 70 electron volt cathode anode here. And as it passes through this point, it's going to collide with an electron at a very high acceleration. So 70 electron volts is strong enough to push out an electron from this molecule, these molecules that pass through. So as it passes through, at this point, it becomes what's called a molecular ion, M radical cation, because one of the actual molecules, let's say there's 2 electrons here, once it passes through the 70 electron volt, it now has one less electron and it's positive. So an electron, or actually 2 electrons get pushed out. One is coming from the 70 electron volt and the other is from this molecule. So essentially this is what we're doing. So I'm going to write just electrons so that you don't get confused thinking 2 come out from the molecule. One's coming from the electron, the 70 electron volt, right? That's the acceleration here. And then it hits this molecule and pushes out an electron. So this is called the molecular ion. So at this point, we have a molecular ion that's passing through. And now it hits this plate. Now this is a negatively charged plate, so it's going to accelerate positively charged species. But things that aren't charged positive aren't going to pass through. So radicals, for example, or things that are not positively charged won't get through this. So if you're a radical cation, no problem. You'll pass right through. You'll keep going. And eventually you'll find your way into this magnetic field. And what happens here is as you pass through this field, as you turn, you either hit the wall, you could hit this wall, or you can keep going straight through and wind up here. Okay? Now, the heavier elements are going to, or heavier molecules are going to wind up hitting the wall at the top. So as it turns, the heavier it is, as it turns, it hits the wall at the top. So this is heavier. The lighter elements, or lighter fragments is what we call them, are going to hit the bottom of this plate over here at this tube, or it'll go out and come in through the light side over here. So that's basically what we're doing. We're detecting where it comes out. So again, this is the basic idea. So you have this vaporized sample, it goes through, it hits, it gets collided with an electron at 70 electron volts, pushing out an electron of the molecule within the molecule. It continues through this path. This is a negative plate, so if it's positive, it gets accelerated through here. If it's not positive, if it's neutral, it just kind of falls out at this point. It doesn't come through. So really, the charge positive is what we're tracking at this point forward, things that are positive. Once it goes through this tube, there's a magnetic field that's going to cause a turn, a curve. And once it does that turn, if it's too heavy, it'll just collide into the wall, but some will get through. It'll find its way here. Lighter will come and hit this side of the wall or come through and find its way over here. And we read that out. Okay, and I'll show you how that is in the next page. So that's essentially the works here. I do want to point out that a 70 electron volt is a very, very, very powerful electron. So it's got a lot of energy. This is a massive amount of energy. A 70 electron volt, let me write that over here. 70 electron volt is equal to around 6,400 kilojoules of energy. Okay, so 6,400. Now, if you want to break a sigma bond, that would require around 400 kilojoules of energy. So think about the collision here. This is a very, very high energy electron. When it hits this molecule, it's going to just collide it, break it apart, and that's going to cause a disruption within the system. And as it flies through this path here, it just breaks up and fragments into different things. So it's a really high energy collision. The other thing I want to point out is that this is what the chart itself is going to be detecting MZ. It's called mass to charge ratio. But our Z, which is equal to charge, is equal to +1. So for the most part, it's really mass over 1, so mass is what we're reading here. So depending upon the mass of the fragment, because it's going to be a +1, not +2, +3, just +1, it'll pass through here, and we can read it on here based on its mass. And that's what we'll see. So the heavier it is, the higher up to the right. The lighter it is, the lower to the left. And that's what we'll see. Okay, so that's essentially what I want to talk about here. Now let's go ahead and take a look at this example here. So here's a molecule, and this is now part of our review sheet. So here's a molecule, and I made it simple. So it's this carbon that has 3 methyls around it. So when you hit it with a 70 electron volt electron, it's going to wind up pushing an electron out of this, and it doesn't really matter where. So when you're not really concerned about where, you draw it in brackets and you write radical cation, because what happens is you're going to pull out an electron, making someone lose an electron, become positive, but it's also going to be unpaired. So there was 2 electrons together, now there's only 1 somewhere. So because we don't care where it is, we just draw it in a bracket, and then we just write outside the bracket a radical cation, which is this right here. Now it turns out that the mass of this and the mass of this are going to be exactly the same. I mean, there might be a slight difference, but not anything that we have to worry about. What's the mass of an electron? It's nothing, right? So in the grand scheme of things, the masses are the same for our purposes. So if you add up all the carbons, hydrogens, it comes out to 58. So that's called the molecular ion. And so if you look at our chart, if we have a chart here, the one that's furthest up here will be 58. And so over here is 0. Okay, so 58 will be the mass of the whole molecule. That's called the M+. And then you'll have this mass break apart. So remember, as you go through this point here, you become M+. But once it kind of accelerates further in and it starts getting propelled through this negative plate, the positive components start to break up even further. These little ions break up. And so by the time you get to the detector, there's many different fragments, not just one thing. So a methyl will break off, but H can break off, another carbon. Really weird things can happen. Okay, so the bigger the molecule, the more things that will happen. But if you look at a chart, you'll see that there's always a lot of things going on. It's not, but it's just the way it works. But in a chart, because of by the way, of all the possible scenarios of things that can happen, so you'll see a whole bunch of lines, but most of them are not really that large and they don't mean anything to us. But the M+ is important. The other one over here, if you could see, it's the base peak. The base peak is going to go up to 100%. So this is the 100, this is 0, and it's based on the base peak. Whatever the largest one going up is, the one that's read the most intense, is considered 100, and everything falls relative to it. So notice that when I broke this one apart, there was a very logical way to do it. I said, okay, well, if I'm going to break this, one side, from here, when it's a radical cation, when you break this, one side becomes a cation, and the other side becomes a radical. So if you break this apart, there's more than one way, right? I could break here. Well, actually, in this case, I made it symmetrical, so there's really one way. If I break here, here, or there, it's the same thing. They're all methyls, right? So if I break here, then this carbon could be either a cation or it could be a radical. This could be a cation or a radical. Remember that our detector only cares about cations, so that's why I'm showing you the cations here. But in actuality, when you break something apart, one side's a cation, the other side's a radical. So in this case, there'd be a methyl radical. And in this case, there'd be a isopropyl radical. Because if there's a methyl cation, then this is the radical, the rest of it. Okay? So the radicals are there, but we don't care about them. Because what we really are going to read are these right here. But it turns out that you can use the radical as a level of importance for you, and we'll talk more about that in the next section. But for now, I want you to see what I did is if you add up the number of carbons, there's 3. So 3 times 12 is 36, and then you have 3, 6, 7 H's. 36 plus 7 is 43, and that's how you come up with this right here, this 43. Okay, and 15, 12 plus 3 H's is 15, right? Each H is 1, and that's how you come up with that right there. There is these numbers over here, and that's called M minus whatever that number is. Now, M minus 15 gives you 43. So remember that 58 is our total, so M equals 58. 58 minus 15 is 43. 58 minus 43 is 15. Now, why is that important? Because what this tells us is another piece of the fragment. So if this is the full molecule, then when this broke apart, we can see this part here as 43, but we could also consider the radical that fell apart, and that's 15. See that? 12 plus 3 is 15. So in this case, 43, because you got, again, the 3 carbons and the 7 H's. So you can see how you can look at it from both points of view, and we're going to use both of them in our learning process, and we'll see that, especially when I do problem solving with you. Okay, let's continue. Oh, actually, one thing I want to point out about this chart. So again, its base peak is the highest, and this is abundance, by the way, abundance. Okay, so we calibrate by the one that goes up the highest. That's called 100% in its abundance, and then everything is relative to it. Now M is right here, but if you have 1 over, that's M plus 1. We'll talk about that next. M plus 2 is another 1 over from there. So if you can have an M and an M plus 2, or you can have an M and an M plus 1, or M plus 1. So these are all based on isotopes that we'll talk about. And remember that this is a MZ, mass to charge scale. And because charge is 1 plus 1, it's always going to be just mass that we care about. Okay, so now let's continue with the common isotopes and common fragments. So isotopes are important because, see, for carbon, there's 2 types. There's carbon-12 and carbon-13. Right? Now, because carbon-13 is only 1%, 1.1, you're really going to see a little tiny bit there. So if you have a chart, and this is just all carbons, you'll have an M, but you'll also have an M plus 1. Now, the bigger this is, then the bigger the M plus 1 will be. So if you have a lot of carbons, then the more probability of having a carbon-13, right? So that's why this gets bigger, and this also is bigger. So sometimes they're really small, and they're so small that you might not even see the M plus 1. It could be like that, right? So you can have, or it could be bigger, and as this gets bigger, then M plus 1 gets bigger. That's for carbon. Now, it turns out that for hydrogen, nitrogen, oxygen, there's not much to it. There's just the one isotope that you worry about. Notice that they're all 99%. So that means that it's so insignificant, its isotopes, we don't even bother worrying about them. Same thing with fluorine. But with chlorine and bromine, they're very special. Because, you see, chlorine, it's a 75 to 25% here. So it's a 3-to-1 ratio. So if you have a chlorine, number one, notice that it's an M plus 2. So one isotope is 35. The next one is 37, 2 bigger. Unlike carbon, which is M plus 1, 12 and 13. This is 35, 37, 79, 81, 2 over, right? So if you have an M over here, and then let's say the next M this is M plus 2 right here, and it's the same height, then you know that's equal to bromine, right? Because they're the same height, that's a 1-to-1 ratio. They're roughly 50%. So 50% of the time, roughly, you'll have this one, the 79 version, and then other 50% or close to it, you'll have the 81 version, right? So that's important. If you see, let's say, M is over here, and then let's say your M plus 2 looks like this, where it's like that, it's a third, this is M plus 2, then you know it's a Cl, that equals Cl, because there is no other M plus 2 that you have to worry about. So carbons are M plus 1, so if you notice that it's 2 over, then it's either Br or Cl, and you could figure it out based on the heights. Okay, so these are things that we'll use. The rest of this fragmentation list here is very common. So first off, everything grows from CH2. So if you go from 3 carbons to 4 carbons, you're adding a CH2. So if you look at the numbers, for example, from C2H5, 29, you add 14 to 29, you get 43. So it's always incrementing by 14. And this is always incrementing by 1 carbon and 2 H's, CH2. Okay, so I did put up CH3 because that is a common fragment. And CH2 I put up as well. Not that you'd see this by itself, but I did want you to see the incremental. This is the one that increments. So you don't really need this chart. You can do the math yourself. I just like to have it. It makes life easier to just quickly reference a range. So if you have a number of, let's say, 82, right, then you know it's C6 instead of H13. Since these are 1 each, you subtract 3 out. So it's H10, C6, H10, and that gets you 82, right? So, it's good to have a little range. These are very common numbers as well. Water is 18. You'll see that come in handy. NH3 is 17. Not so much that we need to worry, but it comes in handy, but not really for our class. This you'll see why, and we'll go through the rest of these in just a few. Okay, but these are your common fragments. All right, let's go on. Nitrogen rule. Now, we really didn't touch much on this, but just so you know how it works, because if you look at nitrogen, nitrogens are 14, right? Oxygen's 16. But the difference between nitrogen and oxygen, or nitrogen and carbon, for example, which these are all even numbers, right? But nitrogen has an extra bond compared to the other guys. So this has NH3, right? As opposed to H2O or 2. So if you have 16 plus 2 H's, that's still an even number. But with nitrogen, because it has 3 bonds to H's, as an example, it will always be an odd number if there's 1 nitrogen, because 14 plus 3 is an odd number, right? It's not an even number. Whereas carbon wants 4 bonds, so it'll always be an even number. So essentially what we're trying to say here is this. If you have an M plus that's odd, then that means that you have an odd number of nitrogen. If you know there's a nitrogen in your formula, then it's an odd number of nitrogens. So it's 1 or 3 or so on. If you have an even M plus, and you know that you have a nitrogen in your formula, like they tell you there's a nitrogen or somehow you figure it out, right? Well, then it has to be an even number of nitrogens. So 2, 4, 6, 8, 10, but even 0 is considered even, because when you have an even number, then it's always a combination. It could always be a combination of oxygen, carbon, and hydrogen. So if you're not sure and you have an even number, and let's say you have a very, there's no nitrogens, right? Then it's definitely oxygen, carbon, hydrogen for sure. If you have an odd number, it's never just oxygen, carbon, hydrogen. There has to be a nitrogen in there. So it really is useful when there's an odd number and you know that there's that tells you there's a nitrogen in your formula. Okay, so O, C, and H will never give us an odd number. So if you have an odd mass number, then it must be a nitrogen in there. Okay, so that's basically how this works, but we're probably not going to use this, but I did want to show it to you in case it, God forbid, came up. Okay, so the last thing we have to talk about now is just different fragmentation patterns. Okay, so now we're going to go in. Here's the first assumption I want you to realize. There's a molecule here, but it's the same thing as this, right? Remember how I said the only difference between this and this is that this is now a radical cation, just lost an electron. So instead of drawing it over and over again twice, save space, I did it once. And here's your 70 electron volt electron, right? So that said, this is now a radical cation somewhere in here. We don't know. It's because it's an alkane. Here's your rule. You always start by considering the cation. So when you break, you could break it here, you could break it there, you could break it there, you could break it there. It can break all these different locations, okay? So you will fragment everywhere because that's just the nature of this. When it breaks apart after being collided by a very high energy source, it just breaks apart into different levels. But there's predictability to it. See, if you break here and this becomes a cation like that, then your MZ is 15. 12 plus 3 is 15. Or 72 minus 15 is 57. So you know 57 is the part that left, right? That's the radical. So in this case, it would just be the rest of this, right? I'm not going to bother drawing all the radicals, but you can figure that out, right? So if this is all that's left and that's positive, then the rest of it's a radical. So you could also break ethyl, right? You could break it here. And if you do that, then it becomes an ethyl radical, and that's MZ of 29. That's the molecular ion right there. Or you can look at it from its point of view of what left, right? What's the other part, the radical? And that's M minus 43. So 43 is the radical part. So 72 minus the radical, 43, gives you 29. All right, you should look at it from both points of view. You'll see why when we get to charts. So in this case, we're now breaking it so that it's still the same break right here between the carbon and this carbon, right? Right there. But instead of this being positive, now this is positive, right? And so in this case here, it's 57. And what left is the radical, the methyl radical, and that's 15, right? So M minus 15 is 57. Okay. Remember, M is always the full mass of the whole molecule. Okay. You could break this way, and you get this, or you could break that way and you get that, right? So these are all the different possible ways to break, and you have to be aware of all these because you'll see every number in the chart, okay? But there's something, remember, called a base peak, right? And we have to figure out what is the base peak. So the way that you figure it out is like this. Here's how it works. You always start by figuring out where's the most stable carbocation. And you could see right here, the branch. This carbon wants to be positive. So it's either this one or that one, because these are secondary cations when you break. The rest of them are primary or methyl. Not as good. So you always start with the cation. And so once you realize, okay, I want to make this carbon positive, how can I break to make it? Well, I could break this way or I could break that way. Now, this is when the radical comes in. So when you have more than one way to make the same degree cation, then you look at the radical for where is it most stable. So if this right here is the cation and I break the ethyl off, then there's an ethyl radical. And that's a primary radical, right? That's more stable than if I break up here a methyl radical. Remember, just like cations, higher degree means more stable. So just remember this trend for cation and radical. Just remember, tertiary allyl is more stable than tertiary, which is more stable than secondary, more stable than primary, more stable than methyl, more stable than vinyl, right? So remember this trend. It's always the same for both of them. So the first order of priority, because what you're putting through this accelerator is the cation, that's the one that you're most concerned about. You want to make sure you get the most stable cation. But if there's two ways to get the same degree cation, same stability, then you go with the radical. Primary is more stable than methyl, right? So that's why the base peak is 43. See that? It's 43 because you make both a very stable cation, or the most stable of all of them, right? And the most stable radical at the same time, right? And that's how you basically do this. All right, so no matter how complex the system is, if it's an alkane, just find the place that makes the most sense to be positive. Okay, let's take a look at B. So for B, we have alkenes and alkynes, and they're kind of linked together. So just like before, we're going to start with an alkene, and the only difference here and here is that we have now somewhere a radical cation. Now, it turns out that we know exactly where it is, but before I show you how that works, I want to just give you the overall process. Your ultimate goal is that you want to find the allylic carbon, That's what you're looking for. And it's either going to be for the triple bond or for the double bond, doesn't matter. The carbon that's next to the pi system, okay? Now, you want to break, so you can either break this way or that way, if you want to break this apart afterwards. So if you break this way, MZ 69, right? 84 minus 15 is 69. So the methyl is the radical, CH3 radical. Or if you break this way, you'll still get the red carbon as a cation, and you'll have ethyl as your radical, ethyl radical. Now, notice that the base peak is 57, which is going to be this right here, right? And why is that the base peak? Because if you look at these are the same, right? These are both secondary cations. That's why I know to do that. That's why I want to break here between these two. And so when you look at this, methyl is not as good as primary for the radical, right? This is methyl and primary. So that's why the base peak is as we see. Now, there's one more possibility, by the way, right? We could have it where it's just one less H. We can have like this, positive, and an H is a radical. But that's not likely, right? I mean, you will see this actually, but it won't be the base peak. It'll be very small because a hydrogen radical is not very stable. So this can happen as well. Everything can happen. But what I'm showing you is actually, and if you look at it, this is tertiary, but because a hydrogen radical, it's not going to be favored over just secondary. So you always want to break carbon to make it the most stable, not hydrogen, okay? So this could happen, but it won't be the biggest peak. All right. So again, so I'll leave that out for now. Now, I do want to emphasize that your strategy is always the same. Look at the carbon that's next to the double bond, and that's where you're going to break from that carbon outward to the next carbon, okay? All right. Now, look, and like I said, these are both secondary, so they're equal in energy, so then you go to the primary. Now, if you did consider the stability of cation, then the tertiary would be best, right? But you don't want to make an H radical. It won't happen often enough. Okay, so that's that. So now, how does this work? Well, here's how it works. And actually, this will show you another level of detail. So just to give you the bigger picture, when you actually collide this, it's always going to be where the radical forms on the actual double bond carbons, because the double bond is the most accessible electron. So when this thing collides, it hits the easiest electron it can find, which is going to be the double bond. So you can have, let's say, a radical here like that and a cation. So what we basically did is we've lost this double bond. We've made a radical and a cation. Now, another thing I want to point out is that you can make it so that the cations, over here, or you could do it the other way around. You can make it where this is the cation and this is the radical. Okay. Now, for the purpose of what I'm going to show you, I'm going to make this the radical and this the cation. And the reason why I'm going to do that is because I want to show you what happens, how the electrons flow. So if this was to go and make a double bond, right? So this is after the 70 electron volts, right? So if this makes a double bond, then you could either make a double bond here and this becomes a radical, right? That's one possibility. So you have that right there. This is still positive, and now you have a methyl radical. Or you can go like this. You can have the positive radical. You can show this become double bond, and this becomes radical. See that? So now you have the other option, which is double bond here, and this is the radical. Still positive there. So do you notice that when you do this, and I didn't mean to make it cis, I just kind of left it, but trans, cis, doesn't matter, but obviously trans is more stable. I'll do that. So notice that I got these two. You see that? These are those right here. Now you might say, wait a minute, you didn't get those two, because look, the double bond isn't on the end, right? See how they're on the end? Well, that's not a problem, right? This is just resonance. So from here, I can just show resonance, and then I'll have the double bond exactly as I show it up above. So if I just simply shift this over, now I'll have what's up above, that right there. And if I shift this one over, I'll have that right there. Okay, let's take a look at C, which is alkyl halides. So with alkyl halides, first off, remember the M+2 for both Br and Cl. For Cl, it's a third the height, and for Br, it's exactly the same height as M+. Okay, so that's important. The second thing I want to point out is that we know exactly where the radical cation forms. It's always on the halogen, because any atom at lone pair is the most likely place to become a radical cation. Okay, just like over here, even though I put brackets here, we know exactly where the radical cation formed. It's the double bond. So double bonds and atoms with lone pairs, that's the place where you lose the radical from, or you make the radical from. Okay, so that's what we have here. And then as far as how you can fragment, well, there's two ways it can go. The first way that you can fragment, I'll do it here so I don't ruin this drawing. The first way to fragment, okay, let me just draw it twice, is where this right here can make a double bond to the carbon that's holding it, while the carbon double bonds as well, and that leaves a fragment behind that's a radical. So we wind up getting that right there. Okay, that's positive, and methyl radical. That's this right here, 63. So remember, methyl's 15. 12 plus 3 is 15. So 15 minus 78 minus 15 is 63. Okay. The other possibility is that the Cl just completely takes off. So if this was to take both electrons and leave, then the carbon would be a positive, right? Because it lost its bond, and the Cl is no longer a radical. It still is a radical, but it has a pair. It took carbon's electron, so it's no longer positive. So now it has the electrons around it, like that, and then one right here. So it's still a radical. Do you see that? Whoops. Okay. So there it is. So that's the two ways that you can get these fragments. So in this case, it's 35, right? Cl's a 35 or 37, but we're always going, remember that this value represents 35, the more abundant isotope. So it's 78 plus 80, and this would be 35 plus 37. This would be 15. Well, this right here would have the Cl, so it would be 63 and 65, right? So you always have that extra 2. But we don't really think about it from that point of view. We look at really just the 35 for the Cl. Okay. So that's it. So that covers this. Just remember that whenever you have halogens, you're going to either make the halogen leave. That's one possibility. And that, by the way, is the base peak here. It's by choice. I mean, by random chance. It could have been that this is the base peak. They both can happen, and they're both having relative stability, right? This is secondary cation, but this has resonance, right? So it's even more stable. But they both can be, sometimes the base peak will be this, other times it'll be that. There's no consistency with this one. All right, but the idea is the same. Either the Cl leaves or the halogen leaves, Br, Cl, or it double bonds to the carbon and right next to it afterwards breaks off. Okay, so now let's look at D, alcohols. So for alcohol, again, we know where it's going to fragment because, or it's going to become a radical cation because of the lone pair, right? So when you hit it with a 70 electron volt, you're going to have this right here, and there's a few things that can happen. Number one, just like the Cl, we can have this become double bond, and then either the carbon takes from here, and that's what we're seeing over here, right? 73. Or it could do it, instead there, it could do it this way, right? And now there's this right here, 45, and then this ethyl, or propyl is the radical, right? So you'd have a propyl radical, or in this case, you'd have your methyl radical. And I hope you can appreciate, in both cases, right, however you break this apart, you could see why this is, or this one is going to be the base peak, because you have resonance stabilization, right? But because this is a secondary and this is methyl, right, these are the same in terms of energy. They're oxygen positive and then the resonance carbon positive, right? But it has like this delocalization. Whereas this is radical secondary, radical methyl, so no surprise, base peak is going to go and be this and this, right, combined. But so the first thing you look at is the cation, and you say, all right, well, they're both resonance. They both have the same stability features. So then you look at these two. All right, what about this? What's this? Well, another possibility, and we'll talk about the mechanism, but not now. So I'm just going to show you the answer, and we'll come back in the next section, or two from here. So essentially what can happen is this becomes water. So remember, oxygen is 16. H is a 1. So 16 plus 2 is H2O, right? That's 18. So M minus 18 is your hint that a water left, and there's an alkene in the system. Now, notice how I put the alkene exactly here. It could be there. It could be somewhere else. But generally speaking, I just put it here as one level of just to show there's an alkene somewhere, okay? And we'll see how that happens in a few. But there's also a radical cation in this case. So when you make the alkene, it also stays as a radical cation. And again, you'll see the mechanism 2 away from now. So let's just leave it at this. But I want you to realize what you could do with alcohol. Either you can make carbonyl, which is these two, or you can make a double bond in the carbon system and get rid of water. And that's what this is. All right? So this is H2O as the radical. H2O radical. Okay? So that's what this is. Actually, sorry, it's not radical. It's just H2O. Okay. So that's it for that one. For E, ketones and aldehydes, well, you have a ketone or an aldehyde, it becomes a radical cation. We know exactly where on the oxygen. And just like with alcohol and alkyl halide, you could make a double bond to the carbon holding it. So this red carbon right there is, or right here, is going to become double bond to it. And there's two options, right? You can go like this, radical, radical, this becomes radical. And that's what we get over here, right? And notice how it's the base peak. You'll see right here is a radical. Okay, or we could do it the other way. We can get rid of the methyl, right? This is a methyl radical. Notice how it's M minus 15, so 86 minus 15, 71. So we know anytime you see 15, it's a methyl, right? And so these are fragments you should be used to, or you can look at my chart that I gave you to summarize these quick things. M43 is 3 carbons. You can see that in my chart. Okay, so why is it that this one's more stable, or the base peak? Because secondary beats methyl, right? These are relatively the same in energy because they're the same thing, right? This is called an aselenium ion, and we'll learn more about them next semester. But essentially, triple bond carbon O, well, this can open up, and now the carbon's positive, right? In both cases, it's primary carbon, right? Just one carbon. So there's no difference between them. That's why we went with the radical. But you always start with the cation. If there's a difference between them, then you know who wins. The only exception to that is if you're losing an H, like I showed you earlier, because then you just don't want to do that. H's don't leave on their own. It's not going to be a common fragment. Okay, so that's it for this. That's how this works. And now the last thing I want to talk about is known as rearrangements. And there are two that we're going to focus on. One is with a carbonyl and the other is with an alcohol. So this is called a McLafferty rearrangement. And essentially what you need to do is you have to have it right here, the gamma. So if you look at the carbonyl, this is alpha, beta, gamma. So essentially you have to make like a 6-membered ring. What happens is like this. So I'll draw the mechanism down here so it doesn't mess this up. So you have this radical cation. And in addition to what I just showed you, which is you make this carbonyl into a triple bond, right, like this. So in addition to this fragment type, this is common. It's not the base peak, but it happens. And so what it is you wind up having this it collides with the H collides with it, this carbon becomes double bond, this carbon becomes double bond, and this carbon becomes radical. So it all happens kind of an electron cyclic flow. Okay, so that's why you need this 6-membered type look to it. All right, so what is the outcome of this? Well, you have a carbon double bond with an H on it now. It's positive, right, because it got an electron from hydrogen, but it didn't get rid of that positive here, right? So it's still positive. And this carbon right here is now radical. And that's what we have up there, right? So if this is the blue carbon right here, blue carbon, there it is. And at the same time, the rest of it becomes an alkene. Because notice how you're making a double bond between these two? So that's it right there. Okay, so that's this piece and that's this piece. So that's all that happens. And so you'll have an MZ, you'll have this reading at 58 in this example, right? So it depends on the carbonyl. But this is a clue. So you'll see how we use this when we do some example problems. Okay, but this is a very advanced topic. You know, I should say not very advanced, but it is an advanced topic. And the only way this happens is if you have a gamma H. So you can't do it in any other way other than if there's a gamma H. Okay, now the similar idea applies for alcohol. So if you look, I basically copy and pasted this, and I just changed it from a double to a single bond O. But the mechanism is very similar. Okay, it's similar. Not exactly the same, but similar. So what initially happens is that this is going to hit the H, radical, this becomes radical. And so now we're here at this point. And now this is going to leave. So this is going to take off and take the electrons with it so that now you have a water over here that's neutral, right? Because it was positive, but it takes the electrons. This is positive now. So you have a radical here and a positive there. This is our radical cation. It's 84. But this will break up even further. And the way it works is this winds up going and becoming a double bond. And now this becomes positive right there. And this becomes double bond like that. So this is your fragment that you'll see. So you wind up getting this little piece here. Okay, so this is a very specific type of breakage. Okay, it's not a very common break, but it happens. And so as you could see, you'll have an MZ of 42. So this is like McLafferty. If you learn McLafferty here, you get the idea of this one, then it's the same thing. It's the same concept, but obviously there's a little bit difference of the break at the end. Okay, they're both important, so I wanted to show them to you. All right, so that covers all of the mass spec review that I want to do. And what I want to do after this now is I want you to try these problems. These are the combination problems. So you should have tried my pre-class quiz examples that I gave you and the solutions to the workshop, because this is more advanced. These are advanced problems that combine mass spec, IR, and NMR. So some NMR, but mass spec and IR minimum. Okay, so pull out your IR chart and your mass spec stuff that you just got now and NMR as needed, and work these problems out, and we'll do them together. Okay, so let's get started. I hope that you had a chance to try these problems. Now, these are more advanced problems, right? So the idea is that you should have practiced your NMR, IR, mass spec workshop, and the pre-class quiz related material. And now we're going to just wrap it up with these last problem types, okay? So this kind of wraps everything up. But these are advanced. Now, these are the charts that we need to have available to us. This is on your front cover. This is my chart. I don't know if you want to use that or not, but if they give you this, then you really don't need that. So we'll kind of work with the general trends. You don't even need this chart. This is my chart, but they'll give you their own version of this, okay? You should be able to see the front cover of your exam, so you could download that and check it out. All right, let's get started. So the first thing is we have IR and we have Mass Spec. Now, I always look at my numbers, right? So my two numbers that I'm initially looking at is this range here. This is around 1700, but 16 to 1800. If I have something that's almost touching the bottom, then for sure that's a carbonyl. So if it goes down a little less than half or halfway down, then it's an alkene, right? Same area. But if it goes all the way almost to the bottom, that's definitely a carbonyl. Now, this is not wide enough to be an alcohol. It stops right at 3,000 alcohols other than carboxylic acids, but carboxylic acids are notorious for being broad, right? They would start before, but they'd cover through like that. So there is no alcohol here, but we do have a carbonyl. This is probably just CH. That's all that is right here for this stuff. Okay, because CHs are on that line. And you could see all that right here if you look at your numbers over here, or you look at my numbers. You could see the general trends. So as far as the mass spec goes, so we know we have a carbonyl, right? And our M plus is right there. M plus is right here, 100. And that's right there. That little dot is M plus 1. So we're dealing with 100. So the total mass, M plus, equals 100. Now, we know that an oxygen is equal to 16. And since I know I have an oxygen from carbonyl, let's deduct that from the 100, right? So we have 84 left over. So I'm dealing with 84. Now, let's look at this little diagram. Where do we find 84? And you could do this in your head, or I like to have a diagram. The closest to 84 is right there. So what I'm guessing is that our formula is going to be C6, H, now this is 85, but we have 84, so H12 instead of 13. Oh, that's the guess of our formula. Okay, we have 6 carbons, 12 H's. Oh, that'll give us 84 for the carbon set, and then of course the 16 will give us 100. Okay, so that's what I'm guessing is our formula, and we're right. That's how you would do it. So you see how I did that? First thing I realized is I have an O in my formula. I got it out of the 100, and then I'm left with 84, and I figure out what's closest to that number, and that's how I work this. All right. So now let's go ahead and analyze a little bit deeper. Well, there's a lot of things that we don't know. Like, for example, we don't know if we have an aldehyde or a ketone, right? That's not clear to us. But we do know we have 6 carbons. So what I'm going to do is I'm going to try to figure out the base peak. Because here's one thing I know. When I have a carbonyl, when it fragments out, the most important fragment is when it becomes triple bond to the carbon and it breaks away. So this right here, this 43, is going to be a carbon that's triple bonded to an oxygen that's positive. And we just don't know how many carbons after that. So let's go ahead and figure that out by just getting the 43 in place. So here's what I mean. I know that from my fragment point of view, this is the most important fragment, right? If you go back to your notes, you can see that in your summary sheet. So what is this right here? Well, this is a 16 for oxygen and 12 for carbon, right? So that's 28. And we need to get to 43. So what that's telling me is I probably have just one more carbon here, like that, CH3, because that'll give me, instead of 12, this is 24 now. Let's redo the math. We have a 24 for the carbon. This is oxygen. This is carbon. And we have 3 H's, right, for H. So that's 13, 2, 3, 43. There you have it. So now I know this right here represents my 43. And you see how I knew it was a carbonyl, and I know the most common break for a carbonyl is where it breaks and it gets rid of one of its sides, right? So the most common break is triple bond O, and then it has R and then the other R, right? That's our common break. So that's where I came from to get to this point. Well, now I know that the carbonyl has a methyl on one side of it, and then a whole bunch of carbons on the other, because that's only 2 of 6 carbons, right? But we're starting to build our piece up. So now I know I have this right here, carbonyl, and I have to have at least a carbon here, right? And that has to have at least a carbon. So now we're down to this. So let's kind of draw out, what are we left with? Well, again, I know this fragment is the base peak, so this is the rest of it. And this is already 1, 2, 3, 4. So my options are 5, 6, or I can have like this, 5, 6, or maybe like this, right? Those are my options. Now, one of these is right. We don't know yet which one, but we're going to see if we can figure it out. Now, notice that the one thing I want to point out is the idea of that McLafferty. If we go back to our McLafferty of carbonyl, we get this 58 reading. See this? When you have a methyl ketone and then the next carbon stays with it, then this becomes the alkene and this becomes 58. You see that? So this is part of that review. Look at our question. Notice that we have a 58. So this right here is the McLafferty, right? So that means that it's this right here. And in order to do the McLafferty, you have to have a gamma H, right? So look at these. This is alpha, beta, gamma. It has an H. This is alpha, beta, gamma has an H, alpha, betas. So this is out. This is out because this one does not have the H gamma that we're looking for. So now we're down to just 2 of them, right? We know, whoops. We know that this one's out. I'll just put it in the box. So now we're down to these 2. Okay. So you see how I figured that out? So the fact that there's a McLafferty reading, this 58, means that I have this methyl and then another methyl. Oh, and by the way, we can go further. See, if it's one methyl, it's 58. But this one, if I break this way or that way, it's more than 58. So I actually know the answer from this. This is the answer right here. This is the answer. And I'll show you why. The McLafferty, if we go back to the McLafferty from our review sheet, the McLafferty breaks. Look at my arrows. This becomes the radical, and then the rest of it breaks off. So we break after between alpha and beta. But in our 2 leftover examples that we weren't sure which one it's from, if this broke here, then you'd have more than 58. You have an extra carbon, extra 14, right? 12 plus 2 H's. So that would actually 3 H's. So this is not going to give us 58. This will give us 58 right there. And this is out because it doesn't even have a gamma. So that's how we solve this problem, okay? So this one can give us McLafferty, the other doesn't. So that's the McLafferty. That is actually this right here, OH, positive, and radical. That's what that is right there. All right, so I hope that was clear. Could you guess what the 85 is, right? This is going to be M minus H2O, right? So that's just going to be somewhere there's a double bond within. Oh, actually, I'm sorry. We're not dealing with alcohol. So no, we can guess. We can't guess it, but we can try to figure it out. But I'm not going to bother. I don't want to make this any more complicated. But do you see how I worked this out? So we knew it was one of these 3 based on the rulings that I showed you. And then we were able to eliminate this one and this one because of the fact that it's not 58. It would be more than 58. All right, I hope that's clear. This is a tricky problem. Again, keep in mind, these are not easy problems. Okay, question number 2, we've got the IR, which really, what this is telling me is nothing. There's nothing that really stands out here. No reading that we care about. There's no OH, right? There's no OH. There's no carbonyl. There's no alkene. There's no alkyne. Nothing. There's really not much given. So it's completely empty in the areas that matter. So there's nothing provided here. All right, so then you go back to here. Well, this is very important, right? Look how this is M. Right here's M. And this is M plus 2. And they're equal, so that tells you BR. They're exactly the same height. So now I know there's a BR, 62, 64. So we have a mass of 162. And if we subtract out BR, remember BR is 79, right? So that's the isotope. Let me put this in. Actually, no, I thought I had. BR is 79. You could take a look at it from your notes. Yep, I just double check myself. So 79, 162 minus 79, if you subtract that out, this is 83. 83 is the number here, right? So think about that. That's right here, 83. That's actually the base peak, right? This is the base peak of 83. So all we're doing is we're getting rid of the BR to get to the base peak, and that's common. We know that, right? We know we do that. So what we can figure out then is if we know we have carbon, hydrogen, and 1 BR, well, what's our carbon, hydrogen? 83. What's closest to 83? C6. So it must be C6 instead of H13, it must be H10, right? Because we're looking for 83, sorry, H11, because we're looking for 83, and this is 85. So we minus 2 from here, H11Br, and that's our structure, right? So now what? Well, okay, here's the thing. Our IHD tells us that if we have C6H11 plus BR's H12, right? So it's C6, it should be H14. We have C6H12. Remember, halogen, you add 1 to the H count. So we have that 2 divided by 2 equals 1. So we have either a ring or a double bond, right? That's what we're dealing with. So I hope this is clear how I use this to get to my number. So ring or double bond. Now we know there is no ring, there's no double bond, sorry, there's no double bond, there's no double bond O, there's nothing in here, right? There's none of these guys. Let me make sure this is clear. So there's no any of those, right? So the fact that we have an IHD of 1 and there is no double bond reading in our IR, we know it's a ring, okay? So now we know it's a ring. So now as far as the rest of this goes, well, 83 is going to be just minusing the halogen, and there's not much more going on. Like there's no methyls being broken off. Like you're not going from 162 back out 15 less, meaning we're not removing methyls. So the chances are that this is telling me that the system is probably symmetrical, or at least, you know, I would kind of guess the system is like this, a 6-membered ring with a BR. Because we know that we have an IHD of 1. We know there's 6 carbons. Now, you might say, well, why didn't you do like a 5-membered ring, BR, and a methyl? Because once you start doing that, now you should start seeing like methyls breaking off. And so you should have a reading for 5 carbons and a BR. But there is none of that, because that would be within this range here, right? So I don't see any of that. So the only thing I see, the first reading up is a BR leaving, but I don't see anything else leaving. Right? So that means that it must be like this, because the only thing you can make leave is the BR, right? And then you have the first major piece, which would be a 6-membered ring. But if I have branching, then this can leave. Like a methyl could break off, or if I have even more, let's say we have a 4-membered ring and an ethyl, then the ethyl could break off, right? So that's why it makes sense that it's a 6-membered ring and the BR. So again, if it wasn't a 6-membered ring, you would have some kind of reading within this range here. So the answer is actually that. It's a 6-membered ring with a BR. Okay? Now you might say, well, what is this 55? What's this 41? You don't have to really worry about that. These are fragments that can happen by making like double bonds in the system, things like that. Like, so if you 55, 83, if you subtract out, you can figure out the difference between them. But you're not going to have to worry, because essentially you knew there was a ring, and you know that the first fragment that you're getting here is the base peak where the BR leaves. The only time that's possible is if there isn't any branches to break off. Okay? And that's why that would happen. Once you have the BR break off from here, then you could do other things. You might break the ring open or other things. But that's why you don't, this is not really important to worry about. Okay, question number 3. We now have a piece of new information, HNMR, right? So we're going to use the HNMR as well in this. So the first thing you do, now when I have a lot of pieces of information, you could start by doing mass, or I like to IR because it's pretty quick, right? So this is really dropping down far, almost to the bottom, so we know it's a C double bond O, right? So now I know I have an oxygen. So this is my M plus right there, and it's 114, right? So if I subtract 16 out of that, if I subtract out my oxygen, then I'll know how many carbons and hydrogens I have. Because the assumption here, by the way, there's no OH, right? There's no OH. There's no broadness over here. So we know there's only one oxygen, right? So if I subtract that out, 16 minus 114 is 98. Okay? 98. So 98. Well, let's go ahead and put this chart in. we're trying to figure out 98, right? Who's closest to 98? Right there, C7H15. So instead of 99, let's make it C7H14, and we're good. We're good to go, right? So now we know. For 98, it's C7H14, right? So our total formula is C7H14. Oh, whoops. C7. See that? See how I figured that out? And that's pretty much, that's all I'm going to do, because I think I can solve the rest of this without going any further into this one. So what I got from Mass Spec is the formula. And normally we have to go further. We got to figure out what this is or what that is. And, you know, carbon, we know that it's carbonyl, so we got to figure out how many carbons. We know it's going to be like this, right? Because we've done this already before. So that would be 43. But we don't really need to do this. And I'll show you why. We have all this down here to work with. Okay? So I'm not going to even bother taking this any further. When they give you an NMR, work with that, right? So what do I see with the NMR? Number one, there's no aldehyde or carboxylic acid, but in our case there is no double O. So, but remember, 9 to 10 is aldehyde, so we don't even get up to, we don't get past 2.5. So there's definitely no aldehyde, right? So we have a carbonyl, for sure, has a carbon on both ends of it, because if it didn't, if it had an H, then you'd have a reading over here. All right. Now, notice that we can read this out pretty clearly, right? There's 2 integration 3. So this is a CH2, a CH2, and a CH3, right? Notice that there's only 3 readings. Well, how's that possible? We have 7 carbons. Symmetry, right? 3 of 7 equals symmetry, right? And we already know that we have a carbonyl. So if we have CH2, this right here, you agree is right next to carbonyl, because whoever's furthest to the left is next to carbonyl. So there's a CH2 next to carbonyl, then there's another CH2, and then there's a CH3. That's it, right? That's all you can do. CH2, CH2, CH3. You can't put the CH3 here, because then there would be a CH next to carbonyl. So it's CH2, CH2, CH3. And since it's symmetrical, let's just do the same thing on the left side. And that's the answer. This is it. So you see, there's only 3 carbons. Well, here's 3, and here's another 3, and then 1 more for 7. This is the formula C7H14. So do you see how I solved that? I hope if you did my NMR work with me, then this was a joke. It's very simple to read this out, because you know carbonyl's here, whatever's next to it is right here, the first one up. Remember, when they zoom in like this, this is a zoom in of one of these readings, which it happens to be this one. Okay, so they're just blowing it up. Don't think this is a reading. See how it's elevated up in the air, and it's got its own numbering? That means it's a zoom in of one of these. That's all. Okay, question number 4. One thing I noticed when I was solving this, I want to do one thing, and I want to point out that this right here, let's start with this IR. This right here should be dropped down further. I don't like that it was so short. The fact that it's more than halfway tells you it's a carbonyl, but we're so used to seeing it go down really far. So I'm going to let you know this is a carbonyl, okay? But because it's a real reading, it didn't go as far down as you would normally expect. But usually when our signature that we've seen always drops down. Just remember that if it's more than halfway, then it's carbonyl, right? If it's halfway, it's an alkene. If it's further, it should have been a little bit further down. So I'm going to go like that and, you know, magnify this or amplify it. And hopefully I'll do that before you see the sheet. So you'll see it on yours. Okay, that's a carbonyl. That's the one thing I want to point out. There's nothing here, right? This is just a CH. There's not broadness here. It's not past 3,000. So really it's just carbonyl. All right, so that said, that's first off, right? So we know we have an oxygen. The second thing I want to point out is look right here. See this right here, this is M, right? Clearly, this is M plus 2. See that? 54, then there's a tick in between 55, then 56. So this is M plus 2. So now I know this must be a Cl because the height of this one is about a third of this one. It's not exactly the same height. So that's another thing. So I have an oxygen and I have a Cl. So from this formula, 154, let's get those out. So remember, a Cl is 35, right? So 154 minus 35 is 119, okay? And from here, now let's minus out 16 for the oxygen, because we know there's an oxygen. And so now we're left with 103. So what is going to bring us to 103? Let's go ahead and pull that up. So we're looking for 103, right? And actually, yeah, that's fine. You guys, so 103 is the number after minusing out the O and the Cl, right? Okay. Remember, when you have HNMR, you're really not going to work with this. We're just going to work down below. So let's go here. So 103, the closest to that, well, this is 99. So if we have C8, remember how it works. You add 2, so H17, and then you add 14, so 113. Right? So that would be the next one down. But you see how this helped you? You didn't have to go figuring everything and making a mistake. That's why I like this little chart. So 8 and add 2, it's always increasing by 2, 13 to 15 to 17. Okay, and then this is increasing by 14, right? So 99 plus 14 is 113. So we're looking for 103. So we know it's going to be 113, right? That's closest to it. It's either adding more H's to something that can't accept them or reducing from one that has more H's, right? So that's why we want to go with this guy. So 113 minus 103 equals 10. So there are 10 extra H's that we're going to remove. So our formula is C8H. Now, remember, we're minusing 10, H7, and then we know there's an O and we know there's a Cl. That's the formula right there. C8H7OCl. I hope that's clear. First, we figured out that there's an O from carbonyl. Then we figured out that there's a Cl from M plus 2. We deduct them from the full mass, and we're left with just carbons and H's, and that's it. Now we're ready to solve this by looking at this right here. We already know there's 8 carbons. Well, the beautiful thing is this tells me right here that I have a benzene. Right? That's a benzene. So let's start with a benzene. And can you tell me how many branches are off the benzene? Remember, there should be, for one branch, 5 H's. And count this up. 2, 4, 5. There are 5 H's. 5 H's. They broke it up for you, but you could add it all together. The benzene range is 5. That means that there's 1 branch off the benzene. So what's off the benzene? Well, we know we have a carbonyl, right? That's told us right there. So we still have a carbonyl. So it's not like it could be an oxygen, then some carbon. It has to be a carbon, right? Because you can't have a Cl because Cl is terminal. So it must be at least a carbon here, right? And now we have to figure out is, well, this is 7. We only have 1 carbon left, actually. There's not much to figure out. It's got to be like this, right? What is our only question for ourselves? Well, number 1, is the carbonyl here or is the carbonyl here? Because look, there's 6 carbons for the benzene. We're dealing with 8 total carbons. We can't have the O as an ether because the O is a carbonyl. So it's going to be like that or like that. It's one of these two. And then we have a Cl to deal with, right? But look, if we put, well, actually, let's go ahead and go further from this. If we put the Cl here, that's a possibility. Or if we put the Cl here, that's a possibility. So these are 2 different possible answers. Let's see if we can figure out which one is which. Well, it says 2 H's, right? This is a CH2. And we have that here, and we also have that here. So that's not going to help us. So it could actually be one of these 2, and I'm not sure if it's clear which one it would be. Let's see. Nothing from here. Well, I guess fragment will help us. Yeah, definitely fragment will help us. Because remember, if you want to fragment the carbonyl, you're not going to break it on a double. Remember, okay, so let's kind of dig into this. Let me pull this down here. This right here. Now, I'm going to show you how to figure this out. The first thing I want to do is this. I want to say to myself, okay, I like this bottom fragment to start with because this is going to be easier to work with. See, well, actually, they're both okay. If I was to fragment this one out, okay, I like this one because it's next to carbonyl. If I was to fragment this out, there's no way. Now, remember, the most important fragment that you get is the triple bond, a carbon that's going to be triple bonded to oxygen, right? But now, if you had to figure out which way does it break off, does it break this way or that way, there's no way it'll break this way, because then you're making a radical on a vinyl position, right? Double bond position. So this must stay together, because you're not going to make a vinyl cation or a vinyl radical, right? Double bond radical. So for sure, it would be like this. This would be the major piece, that plus your CH2Cl, and it's a radical, right? So essentially the way you'd break this is, if you have a radical cation, you would make your, well, let me, that's fine, I'll do it in blue. You go like this, and like that, and then this becomes a radical. And there you have it. That's more stable, radical cation, a radical, than a benzene being a radical. Benzene is double bond, that's worse than methyl. So this is definitely the major, this is the major base peak, okay? If we went this way, then for sure, if this is the radical cation, we would go and do it like this. There's no other option, so you'd get that, right? So our base peak would be like this, a C, triple bond, O plus with the Cl, right? And your benzene radical. So that would be your fragments. Now, maybe this is not so stable, right? But it's the only option that you have. Or you could break off the Cl and leave the rest of this. Yeah, you could do that. But so even if we broke off the Cl, there's an extra carbon here than there is down here. So let's go ahead and figure out what this number is, and let's see if that number, and compare it to this one to see which one is the base peak up here. We're looking for 105. 105 is the base peak, right? So whichever one gives us 105 is the winner. We have carbon, oxygen, hydrogen, right? There are 7 carbons, 6 plus 1 outside, 7 carbons, 1 oxygen, and as far as hydrogens, there's no hydrogen here, right? Because you can see there's no H's here or here. So there's hydrogens here, just 5. Okay, so 7 times 12 is 84. 16 times 1 is 16. 5 times 1 is 5. So here's the total. And if we add this up, it's going to be 103, exactly what we're looking for. I'm sorry, 105. Excuse me. 105. Exactly what we're looking for, right? 105. 105. So I'm suspecting that this is our answer, but just to prove it to ourselves, let's do the same thing here. So if this fragments is 2 possible, either the Cl leaves, which probably makes more sense, right? Rather than a carbon with a Cl and an O and very positive. But if this is the fragment, then it would be carbon, oxygen, Cl. We have 1, 1, and 1. So it's 12, 16, 35, and that would be 63. So that would be a number of 63, which there is no 63. But if, let's say, the fragment happened the way I would suspect, where the Cl left, right? Then if that was the fragment, let me draw that out. If it was like this, the fragment, triple bond O plus, and then Cl radical. Okay, so if this was the fragment, we have carbon, oxygen, hydrogen. I'm not going to have space. Let me put this over here and put this down there. Let me do some blue, actually. 8, there's 1, and there's 5 for the benzene, and then 2 outside, so 7. So 8 times 12 is 96. 1, 16, 7. So 96, 16, 7 add together, 119. Okay, so 119. So 119, if we go up above, well, there's nothing in the 119 range. So for sure, it's confirmed that it can't be this guy, because it doesn't show up in any of these 2 readings that you would suspect. But this one does, right? 105 shows up, and so the answer to this problem is, this guy here. This is the answer. Okay, because that one matches up with the base peak. So you see, this is an interesting problem. These are very difficult. Don't get me wrong. These are challenging problems. But I did want to end with some challenging problems, because we did a lot of these other type of problems that are more straightforward. Just in case, if they want to hit you with a hard problem with all this combined, we're ready for it. Okay, so you notice how if all else fails, you can't get your stuff from here, you're down to 2 answers. Go back up to your mass spec, and then you can try to work it out further with the base peak. Okay, so question number 5. Now, please don't forget to read the statements, because here it's saying chiral. You got to write that out. So that's going to be really important for us. Chiral compound has a strong absorption. This means nothing to us, right? There's nothing there. If it's greater than 3,000 OH, you know, but this isn't telling us anything really. So we'll just kind of leave that alone. 2970 to 2840. If we go to our chart, maybe we could find something, but nothing stands out for me. This stands out, right? Now this is clearly M plus 2. They're equal heights. This is a BR for sure, right? So now we know we have a BR. So our number is our molecule, and let me put this diagram so we can reference it. Okay, so our molecule is total is 136. Let's minus out the BR, right? Let's subtract out 79 so that we can get rid of that BR. So that's 57. All right, so now 57, perfect, right here, right? You see that? So that's why I like this chart, because you have the common numbers right in front of you. You don't have to guess. So 57. So we have a C4H9Br. That is the molecule that we're dealing with, right? So now we've got from that what we need. All right, but now this problem, they're not giving us anything but mass spec and chirality. That's all. So, but that's all we really need. I want to show you why. This is a small molecule. If it was bigger, then it would be a lot more work. But this is actually pretty straightforward. If we do IHD is C4, it should be H12, right? I mean H10. We have C4, H9 plus Br is 10. So it's 0. This is not anything but an alkane that has a halogen on it. Alkyl halide, right? So what are our possibilities? So if I have an alkyl halide, I can have it where it's 4 carbons and a Br like that. Or maybe I have Br here, right? Second in. I can have it where I take the carbon off the end, this carbon, and maybe put it here. If I put it here, it's the same as that, but I could put it here, right? Like that. Or maybe I do the same thing here. I have this right here, Br, and put a methyl right there. So I take this methyl and put it right there on this one, and you get that. That's it. This is all you can do. This is all you have as an option. So do you see how easy this is? Because it's a simple molecule, and it's chiral, keyword. So now this is all you need to know. There's nothing more needed. This is the answer. This is chiral, right? These are achiral. This is achiral. This is achiral. And this is achiral. They don't have 4 different groups around them. So the only possible answer is this one here. Okay? And that's it. So that's how you solve this problem. Pretty straightforward. Question number 6, they're telling us that we have to propose 2 structures because we're not going to be able to hone in exactly. I don't have NMR. If I had NMR, we can figure out the exact structure, but we can get close to it. So the first thing to point out is, of course, right here, this reading right here is a C double bond O, right? And that's all we know. There's no OH anywhere. We don't see anything with an OH. So our mass spec tells us 85, 86. Our mass spec is 86, right? So M is equal to 86. So 86 minus our oxygen, 16, is 70, right? So now where do we get closest to 70? Let's put out our chart, and I can find it right there, right? This is the closest one to 70, C5. So what we're dealing with now is a C5H, instead of 11, minus 1 for 70, H10, and then O. And that's our formula. That's it right there, right? Okay, so we're getting good. And now what? Well, I know that it's a carbonyl, and we don't know if it's an aldehyde or if it's a ketone. We're not really sure about any of these things. But this right here, the base peak, will help us figure that out. So if you look here, it's 40, 41, 42. This is 43. Whoops. 43, right? That's our base peak. So hopefully by now you can kind of get familiar with, if you have a carbonyl, to get to 43, then you'd want to have like this. 43 is equal. Actually, sorry, it's right here. I could show it to you. So it's one of our fragments. This is 43. So now I know, okay, if this is the base peak, and we know that happens with carbonyl, the most important peak, whoops, right here, is where we break from the carbon that's holding the oxygen. So now I know there's a methyl on one side. Well, there has to be at least another carbon on the other side, and we're only dealing with 5 carbons. So now I know it's going to be either like this, or it's going to be like that. 1, 2, 3, 4, 5. One of these two, right? We're not sure which one, but I do know it's one of these two. Now, you might guess this one over this one, but there's no real proof. There's nothing else in here that's going to help us figure that out. Make sure it's clear why we can't go any further, because this is 3 carbons and this is 3 carbons, right? So if I break this off and you make them carbocation, it's still going to be the same 3 carbons. So you're going to get a reading for both of them for 3 carbons, right? So fragment of 3 carbons is going to be around 43, and that's actually the same as the base peak. So there's no real information provided to distinguish between these two. And that's why the problem asks you to propose at least 2 possible structures. All right, let's look at number 7. Same thing. They're telling us to propose at least 2 possible structures, right? So we're going to get ourselves close, but not all the way there. So there's a new reading, and that's right here. What's that right there? So that's right there. If you look closely, that's right around 2200. If we go to our IR chart, this is something that we haven't really pressed on, but you'll see that the alkyne is at 2200. Let's go ahead and take a look. Whoops, where is that chart? Here. So an alkyne is at, well, that's the H. Alkyne is at 21 to 2200. Actually, while we're at it, let's go ahead and look for this. So alkyne H and alkyne, right? So if we have a 3300, we know it's terminal, the alkyne. Let's see if that's the case. Yep, actually it is. So right here is 3300. So between this one telling me it's an alkyne and this one telling me it's a terminal alkyne, meaning an H, so now we have a good place to start, right? So we've got a lot of information. We know that we're dealing with a terminal alkyne. Okay, so now what? Now let's go to our mass spec and work from there. There's no oxygen being provided. There's no alcohol. I don't see any broadness. This is just an alkyne H, but there's no broadness for OH, right? So that's it. That's all we're dealing with is so far what we just said, alkyne. So if we look here, this is my, right there's my M, and so this is M plus, and this is M plus 1, right? So my M, let me move that out of the way, is 65, 66, 7, 68. 68 is M, right? So that's what we're dealing with. Let's take our 68. Let me put it right here. Let's take our 68, subtract oxygen from that. Sorry, oxygen. Why am I saying oxygen? There is no oxygen. So we're good right here, actually. So what's closest to that number? And by the way, there's no oxygen because there's no, carbonyl. There's no OH. So what's closest to 68? Well, 5, right? C5. And we know that, we're going to be less than 71 because there's an alkyne. So if we have C5H, now in this case 71, so we need to subtract 3 from this, right? 68, 69, 70, 71. So H8, C5H8 is the right formula. You see that? So I realize that I have a 68 because I just got the M plus, and this is closest to 68. You don't want to be this one because then you have to add too many H's to get to 68. So this is the right one, and you just subtract out of this whatever's, what you're trying to get to. So 68 minus 71 is 3, so subtract 3 H's from here. Okay, so now I know. Terminal alkyne, and it's just carbons, right? So I think I can probably write this out. It's this. And now the question is it a straight chain? 1, 2, 3, 4, 1, 2, 3, 4, 5? Or is it like that? Definitely terminal, that we know. So it has to be one of these two. And remember what the question said, which one of the two? So these are the possible answers. We're not going to be able to figure out which one because, well, first off, there's too much similarity between these two. So when you break this, you're definitely going to make this allylic, and you want to do that here, allylic. Actually, so let's think about that. So if I break this off, it'll be 1 carbon. If I break this off, it'll be 1 less carbon. So actually, that would do the trick. So let's see if we can figure it out. Let's go a little further. So if I was to go and make this one positive here compared to this one positive, that's the difference, right? Now, I'm wondering if that's going to be, well, the problem is their base peak is just 1H less than M plus. So that means that their base peak is losing the H. So that's going to be an issue for us. I see why we're not going to solve it. So we won't be able to narrow in. If they made the base peak somewhere over here, and then we could figure out, okay, is it 3 carbons or 4 carbons, you know? But in this case, we will have 4, we will have 3, we'll have everything. So it really comes down to just these two. And that's your answer. Okay, so these are the 2 answers that they're looking for. All right, guys. So hopefully this was enough practice. This is really the most difficult that it can get. I wanted to give that to you as just to get you comfortable with as hard as it may get for you. But if you've done all the workshops and pre-class quizzes and all my other work with NMR, HNMR, with IR, you're good to go. Okay? I'll see you soon.